Uh, Good afternoon, everyone. I hope I am audible. So it's 3 p.m. Since it's the first live session, I'll just wait for 5 minutes for other participants to join. We will hopefully start at 3 5 p.m. And everyone is requested to keep their microphone and their camera off. Thank you. So again, I welcome you all to this live session. So I just wanted to say this in case the this link expires after 1 hour, which it does not. I hope it will not. It won't. But in case it does, so you should join this meeting link that I have posted in the chat box. But it won't be needed. Just in case, it's a precautionary measure. And everyone is requested to turn off their mic and also their camera. So we will just start at 3:05. Again, I'm requesting everyone to keep their cameras off. So we'll just start after 1 minute. That's so everyone is requested to turn off their camera. Lokesh, kindly turn off your camera. So it's 3:05 p.m. So I think we should start. So let me just again welcome you all to this live session on the course Digital Electronic Circuits. So first of all, I would like to make a couple of instructions clear. So every week we'll meet at 3 p.m. From 3 p.m. to 5 p.m. and we'll be discussing the sample questions related to the that particular week's tutorial. So I'll be admitting, so some people are joining in, so it's the first day, I can understand. So I'll also make one thing clear is while I'm doing a problem or solving a problem, I won't be able to admit some participants. So the new participants will only be added after a particular problem is solved. I hope that thing is clear. And also after every problem, some time. And one more thing, yeah, I'll just repeat it. And one request, if in case of any, so I'll just repeat the whole things. People have joined in, and please turn off the microphone. So I'll just wait for a couple of minutes. People are joining in, so I'll just wait for 2-3 minutes again. Is that fine with everyone? If I wait for 2 minutes since people are joining, and reply with your answers in the chat box only, yeah? Now I think no one is joining, so let me just give the instructions once again. So first of all, let me just share my screen. And one thing, I won't be able to admit participants now up to the point I solve some problems, then I will admit some new people. So let me just share my screen first. So are you able to see my screen? Any of you can confirm in the chat box. Okay, that's fine. So in case you are not able to see it, just ping me. So let me just give the introduction. So my name is Musab Rafiq. I'm a PhD student in the Department of Electrical Engineering at IIT Kanpur. I am your course TA for this course, Digital Electronic Circuits, that is conducted by this NPTEL, and the course instructor is Professor Gautam Saha from IIT Kharagpur. So every week I'm going to meet you at from 3 p.m. to 5 p.m. on Sundays, and I'm going to discuss problems related to that week's assignment, not assignment problems, some problems that match with the assignment problems or somewhat related to that. So first of all, a couple of things I want to make clear. So I'll be doing these problems, and new participants will only be added after I solve a problem, and I'll also give you some time to ask any questions. But one thing is clear, please make it sure that you have to ask your questions only in chat box, since the number of participants are very high. So I request you ask your doubts in chat box only, and in case I'm not able to understand your doubt in chat box, then I will ask you to open your microphone and ask your doubt. So these are some instructions. And one thing again I'm repeating, I'll be admitting students only after I solve some problem. Like I solve problem first, I'll give some time for to ask question and also admit new participants. So let me just admit some participants and then we can start with the first problem. So Jagannath, I made it clear. You can first try to use chat box in case you are not able to type in your doubt. Then I can ask you to open your microphone, just to keep everything in order. That's the reason. Yeah, Bansari, the lectures are being recorded. In fact, this is a problem solving session. These are being recorded. The PPTs and PDFs will be made available to you, and they will be shared to you from the NPTEL team. Everything will be shared, from recording to PPTs to PDFs of the same thing. So everything will be made available. This session is being recorded. So let me just start with the first problem. People are joining in, I don't want them to miss. So let me just start. Okay, then we can start. I think we can start. So this is a course layout. So this will be available to you. Let me just use a slideshow. So this is the course layout. So in week 1 you guys have studied this TTL logic, CMOS logic, introduction to CMOS logic, and where you use diode and transistor as such. So in this lecture we'll be discussing problems to related to this week 1 material, and also some general concepts of digital electronics, basics, some basics, not that I mean to say not that difficult or anything, just simply basics, one word answer type questions I'll be discussing with you, and also questions related to week 1 material. So this course will be of 12 weeks duration, and 12 live sessions will be done. And also I'll like to mention here that we are 3 TAs that will be conducting this live session, and we are completely individual. So they will also be sharing with you the week 1 material. So you have you can join my session or their session. So it's up to you. You can join all of the sessions, and all of the session recordings and materials will be available made available by the NPTEL team. So let me just start with the first problem. So this is a simply one word type problem. So the question asks us the smaller unit of binary data. Binary data means which can have two values, 0 or 1, is, so out of the 4 options, nibble, bit, byte and word, the smallest unit of a binary data is bit. Is the smallest possible unit we have in a binary data. So what is a nibble? So let me just show you what is a nibble. A nibble is a 4-bit. So 4-bit makes 1 nibble, say another unit. And then we have byte. I think most of you might be familiar with this byte. So 8 bits make up 1 byte. And what is a word? A word is a 16-bit. So 16-bit makes 1 word. So this was the first question. Just some I'll be sharing with you some brief questions for 5, 6. Then I can move to the week 1 tutorial, just to give some insights at this regarding digital electronics. So I'll just admit some participants first. Admit all. Mr. Kumar, Pramod Kumar, can you please turn off your camera? Yeah, Bansari, these will be made available. So since this is the first lecture, everything will be shared. It will be uploaded on YouTube, and a link will be shared with you. No, right now they are not available. Right now, nothing will be available. After this session, after all three sessions are done by all three TAs, then all three videos will be made available, including the lecture material. Everything will be made available. I hope that's clear. Huh? Okay, so let me just start with the second question. Or some people have joined again, so let me just repeat the question number 1. So question number 1 was, the smaller unit of binary data is A. Option A is nibble, option B is bit, option C is byte, and option D is word. So out of the 4 options, the correct option was bit. It is the smallest possible unit of a binary data. Now what is a nibble? A nibble is a 4-bit collection of 4 bits, and what is a byte? It is an 8 bits, and a word is 16-bit. Now question number 2, a 64-bit word consists of A 4 bits, B 4 bytes, C 8 bytes, and option D 8 bits. So in previous question I mentioned with you that 1 byte is equal to 8 bits. So we have question asked us, so what does 64-bit word consist of? So 64-bit consists of, so if we divide 64 by 8, that means 8 bytes. So a 64-bit word is simply a 8 byte. So we have option C, which is the correct answer. Now I'll just admit few participants, and in case someone has any doubts regarding the conduction and all, he or she can ask in the chat box. Otherwise we can proceed to question number 3. And again I'm requesting, kindly turn off your microphone. So let me just discuss question number 3. Can you please repeat the first bit, sir? You want me to repeat the question 1? Hari? Okay. Just write it in the chat box only. No need to open your mic. So question 1 was, the small unit of binary data is option A nibble, option B bit, option C byte, and option D word. So out of the 4 options, the smallest unit of a binary data is a bit, 0 or 1, a single bit. So what is a nibble? A nibble is a collection of 4 bits. What is a byte? Collection of 8 bits. And what is a word? Collection of 16 bit. I hope that was clear. Now moving to question number 3. How many possible values are there for a digital signal? So what is a digital signal? It can either be low or it can either be high. So what does that mean? The number of possible values for a digital signal are 2, either 0 or 1. So option 3, part B is correct. Now these are just simple questions. I just wanted to give some flavor of this digital electronics things. That's why I included these questions here. Now question 4, which of the following statement is not correct? Option A, noise in an analog signal. Option B, variation of resistance in light dependent resistor is an analog signal. Option C, human voice is a digital signal. And option D, room temperature measured during a particular period is an analog signal. So one thing, the reason I put this question here is because some of you will be appearing in exams and all in future. So try to read question twice. The question asks which of the following statement is not correct. So the key here is not correct. You don't have to mark the correct one. You have to mark the one which is not correct. So out of the 4 options, the incorrect one is human voice is a digital signal. So right now I'm speaking, my voice strength, my voice amplitude is continuously varying. It is not a digital signal. It is not consisting of 2 values. It's constantly changing with time. So it's not a digital signal. And all other 3 options, they are analog signals and they are correct. And option C, which was given as human voice is a digital signal, is a wrong option. So the question asked us which of the following statement is not correct. So option C, human voice is a digital signal, is not correct. So this is the correct answer to this question. So let me just admit some students, and in case someone has any doubts, So someone has asked me, please speak in Hindi. Mr. Kumar, I'm not. I think I'm not allowed to speak in. Let me just. This session, I'll just continue with English, but I'll just confirm with the NPTEL team whether I can do it in Hindi or not. So right, this session, I'm sorry, I'll be continuing in English only, because last year I also did my sessions in English only. But I'll just put your query with the central team of NPTEL from IIT Madras, and I'll just ask them whether I can do it in Hindi, because a student asked whether I can do it in Hindi. But I think I won't be able to do it right now. I won't be able to do it. So I'll just continue with English only. But chances are sessions will be in English. This session is definitely in English, but others I have to confirm with the NPTEL team. I'm not sure about that. So Mr. Adil, you asked this. What about option B? So option B is a variation of resistance. It's continuously changing. It's light dependent. As light is changing, the value of resistance are continuously changing. We are not quantizing anything here. So values are continuously changing with time. We have a different set of values if we plot it again with respect to time. So there are no two values. So in digital we have either high or low. So it's changing here. So that's why it's not a digital signal. It's an analog signal in fact. Yeah, I hope I was clear, Adil. Yeah, reply with your answer only in chat box. So I'm just saying, as light is dependent on this light dependent resistor, light variation are there. So will be the variation of resistance. It will be constantly changing with light. It won't be quantized in two values. There are no two values. It will be some. It will be changing. So it's not a digital signal. So now moving forward to question number. Just a moment. One second. I just have to include my camera. It's constantly changing. So slideshow from current slide. So question 4 was done. So the correct answer was option C. Human voice is not a analog. Is not a digital signal. It's an analog signal. So question number 5. Which of the following best describes random access memory? So option A, a type of memory in which access time depends on memory location. Option B, they lose memory when power is removed. Option C, a type of memory in which access time is same for any memory location. And option D, both B and C. So the correct answer to this question is option D, both B and C. So we know this RAM is a volatile memory. So as soon as power is turned off, so the data gets removed, contents gets removed, and also access time does not depend on the same for memory, all memory location. It does not depend on the address. So this is the option D, both B and C are correct. Now moving forward to this question number 6. Let me just take a moment and admit some participants also. I thought some participants were waiting, but no one is waiting. You want Jagannath, kindly wait. I'll just if in option 6 question number 6 you are not able to see it, please confirm it with me. Kailash only, are you able to see question number 6? Can you please use your microphone, Kailash, and confirm with me, are you able to see it correctly? Otherwise I can zoom it. And the circuit part or the question? Okay, I'll just read it out loud with you, and I also draw the circuit because I have to solve it. I'll just draw it below also. Okay, so question 6 asks us, a voltage regulator circuit shown in the figure has following specifications. Vs is equal to 25 4. Let me just draw the circuit first. So a question asks, a voltage regulator circuit shown in the figure has following specification: Vs, that is source voltage, is equal to 24 volts. Vs is 24 volts. Rs, the resistance here Rs, is 300 ohms, and RL is 1 kilo ohms. So the question asks us to calculate the current through the Zener diode having breakdown voltage equal to 18 volt. So what we will do, we will just replace this Zener diode by a 18 volt voltage source, that is by its breakdown voltage. So the circuit will get reduced to like this. This will be the series resistance, this will be the 18 volt source, and this will be the load resistance. This will be 18, this is 24, and this is 300 ohm, this is RS. So the question asks us to find the current through the Zener diode. So we have to find this current. So what we will do, we will just use the Kirchhoff's law. So we will have current going through this resistance I, let's just name it as IS. So it will be, IS will simply be equal to 24 minus 18 divided by RS. So what is RS? So it will be, IS will be equal to 24 minus 18 divided by 300 ohm. So it will be 24 minus 18 is 6 divided by 300. So it will be 6 by 3 raised to power 10 to power minus 2 ampere. So it will be 2 into 10 to power minus 2 ampere. So let me just convert into milliamps. So it will be 20 into 10 to power minus 3. I'm just showing you the every possible step. So 20 into 10 to power minus 3. So the answer will be equal to IS is equal to 20 milliamps. But we are asked to find current through the Zener diode. Now what will we do? We will just find this current going through this resistance, that is IRL. So we will just use Kirchhoff's law here. So IS will be equal to, let me just write it down here, IS will be equal to IG, that is current through the Zener diode, plus IRL. And also we know that VRL is equal to IRL times RL, and VRL is simply 18. IRL we have to find out, and RL is 1K. So we'll just write here is 1. So 1K, just remember this is 1 kilo ohm. So 1 kilo ohm is 10 to power 3. When we will divide it, we will get answer in milliamps. So since I put this in milliamps, that's why I kept it as 1K only. Be careful of the units. So IR will simply be equal to 18 milliamps. And finally IZ will be equal to IS minus IRL. So it will be IS will be equal to, we have found out equal to 20 minus 18. So IZ will be equal to 2 milliamp. So that is option C. So the current source in a diode having breakdown voltage equal to 18 volt in this circuit will be 2 milliamp. So in case of any doubts, any queries, please type it in the chat box. So please zoom questions that I address, sir. This lecture is based on questions and answers or any topic will cover. So Bansari, basically I have taken this week 0 and week 1 this topics covered in week 0 and week 1. So in next session I will be doing questions related to week 2, and it will be mostly on the lines of whatever you will get in assignment, not assignment questions, strictly no assignment questions, but along those lines the questions will be along those lines. Yeah, we can just repeat the question. First I'll just go through all those questions, and at the end I can just repeat it. Because Zener diode is having this breakdown voltage of 18 volt, we have just replaced it by the breakdown voltage. So let me just move forward to this question number. Someone has turned on the microphone. Can you please turn it off? Thank you. So now question number 6 I think we discussed. Yeah. Now question number 7. So question number 7 asks, when transistors are used in digital circuits, they usually operate in A, active region, B, breakdown region, C, saturation region, and cutoff regions, option D, linear region. So in digital circuits, transistors are used as switch, simply switch. Either they will pass the signal or they will block the signal. So that means transistor will be either on or off. So the transistor will be either in cutoff region or it will be in saturation region. Saturation region when we are talking about transistor using digital circuits. So it will be either in saturation or cutoff. So the correct answer to this question is option C. We are either using transistor in cutoff region or in saturation region. It's either blocking the signal or it is letting it pass. Now we have option 8. Which gates are called as universal gates? I think some of you might know the answer, but still we have to repeat it since we are discussing digital circuits course. This is one of the important things here. Which gates are called universal gates? A option is AND gate or OR gate. Option B is NAND gate or NOR gate. Option C is XNOR gate or XOR gate. And option D is NAND gate, NOR gate, and OR gate. So the correct answer to this question is option B. So NAND and NOR gate are called as universal gates, because any other gate can be made by using the combination of this gate, NAND gate or NOR gate. So as a example, I'll just show you NAND gate. Here is the NAND gate. We have input A and we have input B, and we have here Y, and this is my NAND gate. So the truth table will be A, B, C, sorry, Y. So the input combinations that are possible are either both of them are 0, or one of them is 1, or both of them are 1. So NAND gate, what it does is basically the inverse of the AND gate. So when both of the signals is zeros, so its only output is low when both inputs are high. Otherwise, at any instance, the output will be high. So 1, 1, 1, and 0. So this is the truth table of NAND gate. And using this gate, we can construct NOT gate, NOR gate. We can construct NOT gate, OR gate, XOR gate, XNOR gate. So here I'll show you how we use it as NOT, how we'll construct a NOT gate out of AND gate. So we have this A, and I'm using it as second input also, and giving it to NAND gate. So what it does is basically Y is equal to A and A complement, and A and A is simply A, so Y is equal to A complement. Also using NAND gate, we can construct AND gate. So how will we do it? We will just use first NAND. So this is A and B. Then the output, since this is NAND, we are just inverted. So invert, how will we invert using NAND gate? By simply using this circuit here. So we'll just use here another NAND gate where same inputs are applied, and we have a AND gate. Now how will we construct a OR gate? So OR gate will be constructed like this. We have A, B, let me just check it. This is A, this is B, and finally we have this AND operation, NAND operation, and we'll get the OR gate. So what here I'm getting here A bar, that is A complement. Here I'm getting B bar, that is B complement. Then I'm using this NAND gate. So I guess A bar dot B bar whole bar. So using De Morgan's law, so we have this A bar bar plus B bar bar. So we will be having A plus B, that is the OR operation. So here I showed you how using NAND gates I can construct a NOT gate, a AND gate, and an OR gate. So since we have this year we have this live session of 2 hours, I'm just requesting you guys at your own place, if you have pen and paper available, just for 2-3 minutes try using NOR gate, construct OR gate, AND gate, and NOT gate. You don't have to show me the answers and all, just at using your place, at your place. The reason they are called universal, because you can construct any other gate by using combination of those gates. I'm just giving you 5 minutes, just try using NOR gate. I hope you guys know what NOR gate is. Using NOR gate, construct NOT gate, OR gate, and AND gate. That's all for 5 minutes. You don't have to show me the answers and all, just for your own practice. And Akash, can you please type your doubt if you have any doubt? I can see you have raised your hand. Akash, also I'll just try to repeat. I hope that message is still here. Yeah, that is still here, but I'll just dig it up again. So in case the meeting link expires after 1 hour, I hope it won't, I'm sure it won't, but still in case it does, so join this meeting link after 1 hour, but it won't expire. We know that I'll just do it at the end. So I'll just wait for 2 minutes. Till then you can continue with the question that I have given, then we can proceed to question number 9. Okay, I think we'll start after 1 minute. Okay, I can see most of you have completed, so let me just proceed to question number 9. So this thing, last time when I was conducting this course, we had to do this live session for only 1 hour. So that time I was not giving any questions to students. This year I am planning to give some questions to students. So just simple questions along the lines that I am showing in the lecture. so that they'll get involved in the lecture. So I think in this week, since we are at the beginning, so that questions are quite basic. So next time I'll be giving two questions, and I'll also be showing their solutions also. This time I've not done that like. So after next section, after half an hour and 40 minutes, I'll be giving you two three questions. You'll be solving at your own places. You don't need to show any answer, no need to show any solutions, nothing. You have to reply in chat box whether you have done it or not. Then I can show the solution in both ways, whether you do it or not do it. I'll be showing the correct solution afterwards. So this time I have not shown because it was the week one lecture. From next time I'll be just doing that. I think that's a good addition. So now moving forward to question number 9. Question number 9. So this is also a question I have taken up from this week 0 assignment. So this question asks us, we have this 125 to the base r equal to 104 to the base 5. Then what is the value of radix r? So these two numbers are equal, where this number a is in radix r and this is in radix 5. So we are just required to find the value of r. So how will we do it? So we'll just first expand this number 125r to the base r. So how will do it? So we'll just expand it by using this radix. So first at value this, that is 0 1 2. So we'll just write r raised to power 0 multiplied by 1 plus index 1 r raised to power 1 multiplied by the value at that number position plus r raised to power 2 valued by the number that is 1 at that position. And now we'll expand this. So we are having to the base 5. So 5 at position 0 we have this number 4. Then at position 1 we have number 0. So sorry, this is 1 0. And at position 2 we have number equal to 1 only. So these two values are equal. So we have r square plus 2r, r raised to power 0 is 1 multiplied by 5. This is 5. R square plus 2r plus 5 is equal to 5 square, which is 25, plus 0 plus 4. So this is r square plus 2r is equal to 25 plus 4 is 29, 29 minus 5. So r square plus 2r is equal to 24, implies r square plus 2r minus 24 equal to 0. Now let's just factorize it. We have this product equal to 24 and sum equal to 2. Product equal to 24 but it's negative, so that means one of the number will be negative, and sum is positive, so the large number is positive and small number is negative. So we have to just find two numbers whose product is 24 and difference is 2. So product 24 is 8 3 and 6 4. So I think 6 4, yeah, 6 4 24 and 6 minus 4 is 2. So r square plus 6r minus 4r minus 24 equal to 0, implies r common, r plus 6 minus 4 common, and again r plus 6 equal to 0. So we have r plus 6 or r minus 4 equal to 0. So r is equal to 6 or r is equal to 4. R is equal to minus 6, sorry. R can't be equal to minus 6. So r equal to 4. So option A, r equal to 4 is the answer. Here I'll just like to ask you one question, but reply only in chat box. Why r can't be equal to minus 6? So why r can't be equal to -6? Reply with your answers in chat box. Yeah, someone has just answered it. So the radix, they can't be negative values. They are only positive values. So someone has asked a question, can we ask questions from assignment if we have doubt? So basically, if you have doubt, at the end up we might just end up solving those. So we are strictly advised not to discuss those problems, but I'll be discussing problems that are along those lines. So I think that will help with your assignment. So in next week we can just discuss the week 1 assignment. That time I can show you the week 1 problems also. But here I won't be able to discuss the week 1 this exact assignment problems, but I will be showing in the coming questions are along those lines, where I'll be just showing you the problems that are related to those problems, not exactly same but related to those. I think that will help you. I hope who had asked this question, Jagannath, I hope that is clear. So now let's just discuss question number, let me just let's just discuss question number 10. So question number 10 asks, consider the below circuit. The diodes are ideal. So the diodes are ideal. The power supply is of 5 volts and the inputs are 0 volt for logic 0 and 5 volt for logic 1. So logic 0 is represented by ground, that is 0 volt, and logic high is represented by 5 volts. So which logic operation is performed by the circuit? So let's just take the input combination where any of the input is 0. So as any of the input is 0, any of the input is 0, this diode, one of the diodes having that entry equal to 0, will be turned on, and as a result output will be connected to the ground, and as since it is behaving as an ideal diode, so that will be connected to the ground, and my output V out will be equal to 0. So but if all the entries A, B and C are equal to 1, so this diode is connected to high voltage source, that is equal to 5 volt. So these diodes are reverse biased, so no current will flow through it. It will be closed. It will be an open circuit here. So my output at that time will be high. So output will be 5 volt, which we quantify as logic 1. So what we are having here is a case where any of the inputs is 0, my output voltage is 0, and when all of my inputs are 1, that is having high voltage, my output is high, that is logic 1. So if we construct a truth table out of that, so what we have here is any of the input is 0. So let me just construct a truth table for 3 variables, 0 1 0 1, 3 inputs, 0 1 and 0 1 1 1 1 1 0 0 1 1. So what we found out, if any of the input was 0, these diodes will be turned on and the output voltage will be connected to that, and we'll have V0 equal to 0. And also if all the inputs are high, so output will be equal to logic high. So we have 0 0 0 0 0 0 0, and here only output will be high. So what is this? This is simply a AND gate. Option B is the correct answer to this question. So Jagannath says, but sir, 8 sub is a large rate of sum of assignment 1 and 2. It will be helpful for discussing. Yeah, I'm discussing questions along those lines. So right now up to question 9 up to 7-8 questions will be along week 1 assignment lines. So please turn off your camera phone, Mr. Bharat. Yeah, thank you. Adil last, can you please repeat? Yeah, I'll repeat. So the question asks is, consider the below circuit. The diodes are ideal, the power supply is of 5 volts, and the input circuits are 0 volts for logic 0 and logic 1 5 volts. Which of the logic gate operations performed by the circuit? So inputs are given as here. So let me just take any of the combination where the one of the inputs is 0. So as many of the inputs will be 0, the diode will be turned on and the output will be connected to the this ground, that is output will be equal to V0 will be equal to 0 for any of the combination where one of the input is 0. But as this all the input combinations are so all input are given as equal to 1, that is logic 1 equal to 5 volt, so these diodes will be turned off, so the output will be connected to this voltage source, so power supply, so the output will be driven to high voltage, and that is a logic 1. So what we have here is output will be equal to V0 equal to logic 1 for a combination where all the inputs are high, and will be equal to 0 for the combination where any of the inputs is 0. So what I did, I constructed a truth table out of that. So we have these three inputs A, B and C have so I draw a truth table for them. So here we have 0 0 0 0 0 1 and all. So I made 8 possible scenarios. So any of the input is 0, so these 7 cases, any of the input is 0, my output will be logic 0, so that's here. And when the all inputs are high, my output will be high, so that is logic 1. So this is simply a AND gate operation. So in AND gate, for a 2 input AND gate, we have this AND gate represented by this symbol for a 2 input AND gate, A and B. So the output Y will be high only if A and B are 1, and for any of the input combination the output will be 0. So that time I have this truth table 0 0 0 1 1 0 1 1, and my output will be equal to 0 0 0, and when both of the inputs are high, my output will be equal to high. Here the inputs or number of inputs were 3, so it is a 3 input AND gate. So this circuit does the functionality of an AND gate. Sir, is this live session helpful for NPTEL exam? I think obviously whether it's directly helpful or not, but I think you'll get to learn how to solve questions and how to approach a question. I think that will be helpful to you. But it's up to you can watch it or not, but I think it will be helpful. These obviously these live sessions are helpful, and in fact if you still have any doubts for your live sessions, you can just watch the recordings also, and there are 3 TAs for this course. You can just refer to any one of them or all of them, it's up to you. And if you have time, you can refer to 3 TAs, and maybe you can refer to 3 different set of problems that they will be solving. I think that will be helpful, that will definitely be helpful. I think you have recordings will be available only after the third TA will conduct his or her session. Then the NPTEL team, I think, will be upload this. What do you call? They will upload this recordings and all. So now I think we have spent a lot of time for this question. In case of any doubts and all, we will just again be approaching in after some time. When I will solve all problems, we will just be again referring to some problems in case someone has still any doubts. So now just move to question number, where were we? We had discussed question number 10. Yeah, we had discussed question number 10. Now we have to discuss question number 11. In the given circuit, RC is equal to 2 kilo ohm, RB equal to 1 kilo ohm, and VCC equal to 5 volt. Find the value of V out when VA equal to 0 volt and VB equal to 5 volt. So since we are dealing with digital electronic circuits, and you guys have referred the lecture, you might have seen these circuits at individual levels. So if you go on solving at circuit analysis doing at individual level, you might end up having a trouble in solving. So you need to take care, you need to look individually these blocks, what are these blocks, and then approach the circuit solving. So I hope you guys have referred to week 1 lectures. So let me just show you how to approach and how to solve this problem. So let's just take this block first. So these are my two inputs, VA and VB. So what is this block basically doing? If you carefully examine it, when both of my inputs are equal to 0, my diodes are off, there is no conduction, the diodes are reverse biased, there is no conduction through them. So this transistor is in cutoff region, and as a result my output here will be high as it's connected to VCC, correct? So after that if my any of the inputs is high, my diodes will be conducting, and as a result the current will flow through this direction, and this transistor will be on, and this point will be connected to the ground, so it will be driven to logic 0. So that means my output will be low. So what I am saying is, if my both inputs are high, so these are in diodes are reverse bias, so there will be no conduction, this transistor will be off, my V0 will be high. And when any of the diodes are on, so when is diode on? When V or VB is any of them is equal to 1, or both of them are equal to 1, so this transistor will be on, it will be in saturation region, and this will be connected to the ground, and my output will be equal to low, correct? So what I am getting here is VA, VB, so I am getting it here is 0 0 0 1 1 0 1 1. So my output, V output for this only, I'm considering this block only, I'm not taking this block only, will be 1 0 0 0. So this is logic high. So which gate is it? Which gate is it? Is an OR gate. Now take up this block. Here we have this. So what I am having here is, so if my any of the inputs is 0, any of the inputs is 0, this diode will be turned on, as a result the current conduction will be like this. If any of the input is 0, current conduction will be like this, and this diode will be off, and my output will be at high. So what I am saying is, if VA or VB is 0, or both of them are equal to 0, the diodes will be turned on, and current conduction will be like this, and my transistor will be Q1 will be in cutoff, and my my output will be high when any of the input is 0. And when both of them are equal to 1, so this will be cut off, and my current will be going through this base, and this transistor Q1 will be turned on, so my output and this point will be driven to ground, and my output will be low. So what I am having here is A B 0 0 0 1 1 0 1 1, and this is my output, V output. So when I said when any of the inputs is 0, or both of them are equal to 0, these will conduct, and as a result this transistor will be off, and so my output will be equal to high. And when both of them are equal to 1, my transistor will conduct, and this point will be connected to ground, and so my output will be low. So which functionality is this? This is NAND gate. So this is NAND gate. And what is this block? I think people who have referred to the lecture will directly say it is a NAND gate. Is using this transistor logic, and Professor Sai has shown this in lecture 3. So if you want to see its working and all, you can just refer to 3. And in fact, out of this circuit, in lecture is also shown here that by replacing these two diodes by the multi-emitter source, and by replacing this level shifter by a phase splitter, you get a transistor logic. So this is also a NAND block. So what we are left here is, we have a NOR block, 2-input NOR block, 2-input NAND block, connected, whose outputs are then connected to NAND block. So we can, let me just introduce a blank slide here. So we have a NOR block and then NAND block. So we have a NOR block, we have a NAND block whose outputs are then connected to the NAND block. So we can just draw the circuit like this. We have a NOR, A, B. We have a NAND, A and B. Both of them are connected to another NAND block, and here is our output. So the question asks us, my output is V equal to 0 volt, that is logic 0, and my VB is equal to 5 volt, that is logic high. So this is 0, this is 1. So when any of the input is 0 for a NOR block, the output will always be equal to 0, and when any of the input is 0 for a NAND block, the output will always be equal to 1. Now we are left with this block. So this NAND block gets an output input 0 and input 1. So when any of the input is 0 for a NAND block, the output is 1. So the output output Y is equal to 1, and in terms of the voltages, V out will be equal to 5 volt. So the answer to this question is 5 volt. Avinash Kumar, I think this was cathode voltage is high with respect to anode, then the diode is upon 7, then how to get output high. I think this was related to question 10. So I'll just repeat that question in the end. Some of you are also asked to repeat it. I'll be just going so those questions at the end also. Yeah, question 9, I got it. It was related to question 10. I'll just repeat it in the end also. I have a couple of questions to repeat again. So right now I'm just going through all the questions and asking some. Sir, tomorrow's session will be different class or same class? Tomorrow's session will be based on week 1's tutorial only. Week 1's question related to week 1 assignment, but it will be a different TA. There are 3 sessions, na? Sunday, Monday and Tuesday, I think. Third is on Tuesday, right? Can you just confirm that? So it will be by different scholars from different institute. They will be conducting this session. But material topics range will be pertain to only week 1. They can't go into week 2 and all. We have to just stick to the week 1 material only. That's the guidelines we have been given. So next time I'll be just discussing with you week 2 material. This time I'm discussing with you week 1 material, and next time I'll be discussing with you the week 2 material. This time I'm discussing with the week 1 material. So now let's just move on to question number what do you have to discuss? Question number, where were we? Question number 11. Now question number 12. So the question number 12 asks, in the given circuit, find the value of your output when VA equal to VB equal to 0 volts. Here the inputs are applied to these diodes. VA equal to VB equal to 0 volt, when VA equal to VB equal to 5 volt, and when VA equal to VB equal to 1 volt. So when VA equal to VB equal to 0 volts, this diode is on and this point will be connected to here. So both it will be driven to ground, and here we have only 0.7 volt, and it won't be able to turn the diode on. So what we have here is output will be equal to 0. So this is on, this is on. You can see the current conduction will be going like this. So this won't be turned on. So these points are connected to this will be the low resistance pass there, and as a result my output, no current will be flowing through there, so my output will be equal to 0. So in case first where input VA equal to VB equal to 0 volt, my output will be 0. Now the second case where input are equal to 5 volts and 5 volts. So when we apply 5 volts here and 5 volts here, these are reverse biased, and we have 5 volt here. So we have 5 volt here connected here, then we have RH here, then we have this diode, and we have this RL. So this diode will be replaced by the drop across, this will be replaced by this 0.7 volt. So we will be having this, we have this here as 5 volts, then we have this RH, and then we have this diode drop of 0.7 volt, and then we have this RL. So this is RH, this is the diode drop of 0.7 volt, this is the RL. So the current that will be flowing, we can just use the Kirchhoff's voltage law. We will have it like this: 5 minus IRH minus 0.7 minus IRL will be equal to 0. That implies 4.3. 5 minus 4.7 is equal to 4.3 is equal to I times RH plus RL. That implies I is equal to 4.3 divided by RH plus RL. So what is RH? RH is 2K, and what is RL? RL is 10K. So I, that implies I will be equal to 4.3 divided by 10 plus 2. Minded these are in kilo ohms, so I'll be getting my answer in milliamps. So 4.3 by 12. Let's just keep it like that only. 4.3 by 12. So what will be my voltage? That is will be equal to voltage V naught will be equal to I R L. So it will be 4.3 by 12 multiplied by RL is 10. So it is 43 by 12. So that is 43 divided by 12. That is 3.583. So for case 2, my V naught is equal to 3.583 volts. Now case 3, where VA is equal to VB equal to 1. So where VA is equal to VB is equal to 1, voltage at point X. So what is voltage at point X? So voltage at point X will be 1 plus the drop across this diode. So it will be 1 plus 0.7 volts. So since we are given this, the drop across diode is equal to 0.7. So equal to 1.7 volts. So and also the drop across this diode is 0.7 volt. So the voltage V naught will simply be equal to 1.7 volt Vx minus the drop across diode DL minus 0.7 volt. So for that case we will be having 1 volt. So my third will be equal to 1 volt. Here what I did this as both of the inputs are equal to 1, and so that means the drop across potential at Vx point will be equal to 1 plus the drop across the diode D1. So that is 1 plus 0.7, that is 1.7 volt. So Vx will be 1.7 volt, and V naught will be equal to 1.7 volt minus the drop across DL, that is 0.7 volt. So 1.7 minus 0.7 volt, so it will be 1 volt. So my combinations for input combinations, these 1, 2, 3, I am getting output voltage as 0, 3.583 volt and 1 volt. So this is option V0 is equal to 0, V3.583 volt, and this is option A. So question 12, the correct answer to this question is option A. So Kailash Kumar has written only one each week. So Kailash, can you please elaborate your question? And Mohit, how many days class will be there in 1 week? So are you talking about this live session that I am conducting? So Mohit, I'll be doing one live session per 1 week individually, and there are also 2 other TAs. They'll also be doing one live session per week. So in total there are 3 live sessions conducted by 3 different TAs. So there are 3 live sessions conducted by 3 different TAs, but there'll be 3 live sessions conducted by 3 different TAs pertaining to that week's lecture only. So here we are discussing week 1 material. So the other TAs will also be discussing questions related to week 1 material, and on next Sunday that is I think on 12th I'll be discussing questions related to week 2 material, and they'll be also discussing questions related to week 2 material. So Vinod asked me to explain once again, and Kailash, can you please write boldly unable to visible, unable to see. Sir, please explain question. Yeah, Avinash, I told you earlier that I'll finish the questions. If there is time, I'll just repeat all questions where you guys were having doubts. I have that in mind. You asked about question 10, and the other guy asked about question 9. So I have that in mind. Don't worry about that. So Vinod asked me to read question part number 3. So Vinod, as we are having this V and B equal to 1, so we have 1 volt here and 1 volt here. And so the drop across diode, since it's forward bias, it is an ideal diode. Sorry, it's a drop across diode will be 0.7 volt. So 1 is here, so we have this like this, minus plus. So we have 1 volt here, then we have uh, 1 volt here, then we have, so this is Vx. So this is 1 volt, this is 0.7 volt, so the Vx will be 1 plus 0.7, so this is 1.7 volt, and this also will be having a drop of 0.7 volt. So 1.7 volt minus, here it will be like this, 0.7 volt. So 1.7 volt minus 0.7 volt, so it will be 1 volt here. So the voltage across output will be 1 volt. Now moving forward to this question number 13. This is a here the question asks us to match column A entries with column B entries. So we have to match this column A to their right answers in column B. So option A, what is option A? So multi-emitter transistor Q1. So this you know is this TTL logic. In lecture 3 and 4, Professor Shah has discussed this thoroughly. So the question asks us, what is the job of multi-emitter transistor Q1 here? So this multi-emitter transistor, among the following option, helps in steering current from the base of Q4. So either it will drive current towards Q4, or it will take current away from Q4. So this transistor, multi-emitter transistor Q1, acts as a current steerer. So this is option A, will be connected to 2. So then we have transistor Q4. So transistor Q4 acts as a phase splitter. So in diode transistor logic, we had the diode. Here we have this phase splitter. Professor Shah has again mentioned this thing in lecture 3, thoroughly has discussed there. So you can just refer in case someone has not referred, but most of you might have referred it, so you guys will be able to understand it thoroughly. Then we have this diode D1 and D2. Why are these diodes D1 and D2 used? They are used to prevent ringing. So option C is 4. So what is ringing? Ringing is the fluctuations in the signals. So by using these diodes, it maintains the input at two possible levels only, that either high or low. Otherwise there will be some fluctuations in the input voltage levels. So but because of using these diodes, it will either be equal to 0 or it will be equal to the high value. And then finally this diode D3, it is used as the level shifting. Because of this diode D3, this transistor Q2 either remains off, so that the output is not changed. This thing is again explained thoroughly by Professor Shah in lecture 3. So what we got finally, so option A, that is multi-emitter transistor of Q1 is used as a current steerer. So it takes away, or it gives current towards the base of the Q4. So transistor Q4 is basically used as a phase splitter. Diodes D1 and D2 are used to prevent the ringing, and finally diode D3 is used as a level shifter. So yeah, Avinash, I think he is not hearing. I will explain question 10. So Kailash, Avinash, question 10. Avinash, Kailash asked, sir, from where you are live session is taking. So Kailash, I'm not able to get your question. Can you please repeat or reframe it? Kailash, I hope I'm audible. I'm just. Can you please rephrase your question? So okay, I'll come to your question, Kailash, after this. After I answer question number, where are we? Question number 14. Right now, I'm not able to get your. What are you asking? So let me just solve question number 14. So this. So let me just ask a question here. So this circuit that you see below is based on which logic family? Just a simple question. If some of you, any one of you can answer this. Is based on which logic family? I just wanted to make a slightly interactive, as it's a long session and some of you might have lost some attention. That's why. So this is based on which logic family? Can anyone of you comment? Yeah, CMOS. Correct. And can anyone of you tell me that here you can see 1, 2, 3, 4, 5 blocks are there. What does each block represent? Okay, now I'll show you and then I'll ask you a question. So let me just show you the question. So the question asks to consider the following circuits with input A, B and output V0. The logic gate implemented in the circuit is, so we are given with these options and we are asked to show which logic operation is implemented by this circuit. So if you carefully examine this circuit, all blocks, by blocks what I mean, this circuit block, this circuit block, this circuit block, this circuit block and this circuit block, they are same. See, two PMOS connected in parallel and two NMOS connected in series, and here we have the output. Two PMOS connected in parallel and two NMOS connected in series, here we have output. So these all are same. So what is in this individual block? So this individual block is so we have these 5 blocks here and this is the block. They are all made up of this block. So this is the block. So what is this block essentially does? This is a NAND gate made up of the CMOS logic family using CMOS technology, CMOS logic. So what have we here? So as input A and B are 0 0, so these two NMOS transistors are off, and A and B is 0 0, so this point VDD gets connected to V0 and my logic is high. So 0 0, my logic is high. And A is equal to 0, B is equal to 1. So A is off, B is 1. So this is again, there is no power to discharge. So this point V0 will be charged to this. So A is 0 through this point and this will be equal to again 1. So 1 for 1 0 also the same, and when both inputs are high, so that is 1 1. So this pull up network will be turned off and pull down network will be turned on, and the output will be discharged via this path. So I'll be having 1 1. My output will be equal to 0. So this is my NAND gate. So this is a NAND gate. This is a NAND gate. All of them are NAND gates. So let's just quickly examine. So let me just mark here. This is 1. This is 2. This is 3. This is 4 and this is 5. So input A and B are connected as two inputs for a NAND gate block 1. So this is like this. I'll just separate it by the symbols now. These circuits I'll just replace by the symbols. So this is 1 and this is my A and this is my B, and the output here of this first block is here, is connected as an input to second NAND gate, and whose another input is A. See, you can see goes to NMOS. So this is connected to another logic gate whose number I have just given as 3. And also you can see the output of this 1 is connected to another NAND block whose another input is connected to B. So this here, this is 1, this is 2, this is 3. Now 4, what is 4 having? 4 is containing inputs from output of 3 like here, and output of 2 like here. So these are the two inputs for 4. This is 4. And what is 5 essentially doing? 5 is taking the input of 4 and applying it as input. So the output of 4 is given as both inputs to 5. So it will be like here. So this see output connected to a first input, the same output connected to the second input. So it will be like this. So this is how I reduce my circuit to this schematic. So I'll just introduce another slide and there will be solving this circuit. So where is it? So here I was having 1, so this was A, this was B. So let me just now mark the individual outputs. So this will be X1, this will be X2, this will be X3, this will be my X4, and finally I have the output which I will call it as Y. So what is X1? X1 is simply NAND of A and B. So it will be A, B whole bar. So this is output X1. So what is X2? X2 is simply this output and this. So our X2 is equal to X1 dot B and B whole complement. So which implies it is equal to X2 is equal to B dot B and. So when I am saying dot, take it as a NAND operation. So dot means NAND operation, AND operation, sorry. A dot B complement and then whole complement. So this B is here and this X1 is AB bar. So then we have X3. X3 is equal to, X3 is A, so A dot, so X1 and then whole complement. So just writing it as A, so X1 is AB bar and then whole bar. So here using the De Morgan's law, so De Morgan's law states that A dot B bar is equal to A bar or B bar. So this dot represents an AND operation and this plus line here represents an OR operation. So B dot AB bar will be equal to, using De Morgan's law, will be equal to B bar plus AB bar and then whole bar. So B bar will remain as B bar, so B bar means B complement, so AB bar then whole bar. So we know that A complement whole complement is simply equal to A. So here A is equal to AB, so AB bar whole bar will be equal to AB. And also for this also, so A dot AB bar will be equal to A bar using De Morgan's law, plus AB bar whole bar, so it will be equal to A bar plus AB. So these are my x2 and x3. Now the coming for this logic gate and AND gate 4, so x4 will be equal to x2 plus x3, sorry, x2 dot x3, and so x2, what is x2? x2 is B bar plus AB and what is x3 is A bar plus AB and then the whole complement. Now again using De Morgan's law, so we have here A dot B whole bar, so it will be equal to B bar plus AB then bar so something is not B bar plus AB whole bar, and then it's A bar plus AB whole bar. Now again using De Morgan's law, so De Morgan's law is another form where we have this AB whole bar is equal to A bar dot B bar. So here we have this B bar whole bar dot AB bar plus A bar whole bar dot AB. So if I write the A term first, so it will be A dot AB bar plus B dot AB bar. So this is my x4. So this is my, this thing is my x4, and this x4 so my x4, let me just write here, so my x4 is equal to A dot AB bar plus B dot AB bar. So this x4, as you can see here x4 goes to NAND gate. If you remember early on, I showed you this NAND gate. When you use it is like this, it becomes an NOT gate. So this x4 is like this and it goes to the NAND gate. So what it does is, so let's just say if my input was here x4, this will be x4 bar, so my output will simply be equal to x4 bar. I showed you earlier that this is a NOT gate, so my output will be equal to x4 bar. So my x4 is A dot AB bar plus B dot AB bar, then it's the whole bar. Again using De Morgan's law, so it's A dot AB bar whole bar and with B dot AB bar whole bar. Now using De Morgan's law for this block and this block, so this is A bar plus AB bar whole bar. Now using De Morgan's law for this block, so this is B bar plus AB bar whole bar. So this is equal to A bar plus AB, and this is equal to B bar plus AB. So what I get here is A bar B bar, then A bar A B will simply be equal to 0 because A bar A times A bar is 0, so that term will be 0, and then A B B bar will also be 0, and finally I'll have this AB. So what I'm getting here is my Y, my output, will be equal to AB plus A bar B bar. So this is nothing but a XNOR gate. So but question asks us what it does. So we have this Y equal to AB plus A bar B bar, Y equal to AB plus A bar B bar. So option D was correct answer to this question. So sir, CMOS condition, yeah, all not important condition, that's true. Most of the doubt is clearing in this live session, sir. Okay, I hope this question was clear. It was, I did it, I elaborated it. I just wanted to show it in detail, that's why it took some time. I just wanted to show it in complete detail. So I hope it was clear, huh? Acha, you were saying from where you are giving this live session. Yeah, now I got your question. So you were just asking me where are you giving this live session, yeah? So right now I'm in my campus, IIT Kanpur campus. I am in my IIT Kanpur campus. Yeah, I belong to Jammu and Kashmir. If you are particular about that, where state I belong to, I belong from Jammu and Kashmir, and right now I'm here at Kanpur, IIT Kanpur. I'm in campus. So I think no doubts related to this question. So I think we can proceed to question number, this was question number 14. So I think we can proceed to question number 15. Yeah, we can proceed to question number 15. So question number 15. So for a given transistor circuit, the time it takes to change the output from high to low is 25 nanoseconds, and also the propagation delay of the same circuit is given as 32 nanoseconds. What is the approximate time interval that a circuit will require to change the output from low to high? So we are given this propagation delay and also the delay it takes from going from high to low. Now we are required to find the time interval it takes to go from logic low to high. So if you have clearly gone through the lectures and all, we are having this, let's just say our input makes a transition like this, high to input makes a transition like this from low to high, and output makes a transition from high to low, high to low to high. It's going from low to high, and then it's going like this, and it's going like this. So we measure this transition from 50% point where the output, so this is where the output is going from low to high. So this is TPLH. So the point where I'm marking this, it's a 50% point here, 50%, where let's say the signal goes from 0 volt to 5 volt. So this point here is 2.5 volts, and here if a signal goes from 0 volt to 5 volt, so that's point 2.5 volt. I am marking those 2 points, and the time difference between those 2 points I am terming it as TP low to high, where the output goes from low to high, and this is TP high to low, TPHL. And the propagation delay, TPD, is simply equal to TPHL plus TPLH divided by 2. So what are we given here is, so propagation delay of the same circuit is 32 nanoseconds. So we are given it as 32, and TP high to low is also given as 25, and we are required to find out this entity, that is TP low to high. So divide by so this is a simple one variable equation, so we'll just solve it. So it will be 32 times 2 is 64 equal to 25 plus TP LH. So that implies TP LH will simply be equal to 64 minus 25. So this TP LH will be equal to 39. How many seconds? 39 nanoseconds. So units are important. This is my advice, whether whenever you are appearing for any let's just take exams out of it. Whenever you are doing any problems, whether you are doing it on rough or you are doing it appearing for exams, or you are doing anywhere, don't forget to mention units. These are this is an important thing. Don't forget to mention units. So the approximate time that would require to change output from low to high is 39 nanoseconds. So the correct answer to this question was option C. So Raju asked a question related to internship. Sorry Raju, I'm myself a student. I can't help you with that. You can ask. There are some other mediums where you can get the internship. Unfortunately, I'm not one of those. Kailash asked the good book for digital electronics, Morris Manu, and also Professor Saha's book is here. But I have in my BTech days I have referred to Morris Manu. Morris Manu is good book. Morris Manu is good book. You can also refer to these NPTEL lectures. These are really good lectures. IIT professors are teaching you. If you go through these lectures thoroughly, it will be really helpful. They are really good professors are teaching these lectures. So you can refer to these lectures. The book is Morris Manu and Professor Saha's book is there, and also you can refer to some. There are some verified channels on YouTube which you can refer. But I must say, whenever you are referring to YouTube, just see the source, because right now there are thousands of people are uploading these lectures. So always go for a verified source. You might feel that some people is showing some tricks and all, but not all those tricks are right. Try to refer to the YouTube channel which is verified and has some credibility. Morris Manu, I can refer to the, let me just pull up the exact name. These are the two books. Professor Saha's book is also there, and the Morris Manu. I had referred Morris Manu in my BTech days. I had referred Morris Manu. Both books are really good. I have not referred one, but Morris Manu I had referred. So internship opportunity, I addressed that. I also gave you the book name in the chat box. Now I think I can proceed to question number. Which question I have to discuss? 16. Okay. Question number 16. So in the given circuit, RB is equal to 20 kilo ohms, RC is equal to 4 kilo ohms, beta is equal to 100, VB on is equal to VB sat is equal to 0.7 volts, and VC on is equal to 0.2 volts. Find the value of the noise margin, transition width, and the output swing, logic swing for input output characteristics of the transistor. So in fact earlier on also I told you, whenever the transistor acts as a switch, it operates in two regimes, either in cutoff or in saturation. So when the transistor, let us call it transistor Q1, is at the edge of saturation, when this transistor is at the edge of cutoff, so which means to say when the input slightly increases from that point, it goes into different region and it's not in the cutoff region, we call that point as VIL. So VIL is equal to V in at the edge of saturation. So this is simply equal to 0.7 volts. Greater than that, the transistor will turn on, and we won't call it as this. it won't be in the cutoff region. So at the edge of the cutoff region, we call this point as VIL. And then at the edge of the saturation region, the current IC that is flowing through here, IC will be equal to, here this voltage VCC, will call it as VCC. IC will be equal to VCC minus Vsat on. So Vsat on is 0.2 volt, VCE sat divided by the collector resistance, that is RC. So the IC will be equal to VCC, here is 5 volts, and VC on is given in saturation region, at the edge of saturation. This is at the edge of saturation, this was at the edge of cutoff region, is 0.2 volt. And RC is, how much is RC? RC is 4 kilo ohm. So IC will be equal to 5 minus 0.2 is 4.8 divided by 4. So 4.8 divided by 4, 4.8 divided by 4 is 1.2 volt. Sorry, 1.2. What is this? Since the resistance was in K, so this will be milliamps. Take care of these things. So sometimes you might confuse this with ampere and all. This is 4 kilo ohm. It was 4K. So that is 1.2 into 10 to the power minus 3 amperes. So that is 1.2 milliamps. And what is beta? What is IB? So IB is simply IC by beta F. So IB is equal to 1.2 divided by 100. So that is 0.012 milliamps. So then we can have V in minus IB RB. So applying this KVL here, V in minus IB RB, and also the transistor is on, minus VB on is equal to 0. So what is VB on? It's 0.7. So V in is equal to IB RB plus 0.7. IB I found out 0.012 multiplied by the value of RB, that is 20. So 20K, but here I am milliamps, so it will give me answer in volts. Units are satisfied, and this is 0.7. So 20 into 12 is 240. 24, 240, 2.4 plus 0.7. How much is it? 2.4 plus 2.4, 0.7. Okay, this is 0.27. Okay, 20 into 0.12. Let me just check it. 20 into 0.0. Okay, 0.24. 0.24 plus 0.7. So this will be equal to 0.94. So this will be my VIH. And VOL is simply VCE on. So VOL will be equal to 0.2 volt. So what I have found is VIL to be equal to 0.7 volt, VOL equal to be 0.2 volt, VIH equal to be 0.94, and VOH is simply VCC, that is equal to 5 volt. Now the question asks us to find the noise margin. So let me just use the new slide. This is VOL, this is VIH, and this is VOH. So the noise margin high will be equal to VOH minus VIH, that is equal to 5 minus VIH is how much? 0.94, that is 4.06 volt, and noise margin low is VIL minus VOL. That is, VIL is how much? 0.2 volt minus 0.2. VIL is how much? Let me just check it again. VIL is 0.7 volt. This is 7.7 minus 0.7 minus 0.2. So this is 0.5 volts. So my noise margin is 0.5 volts. So how much is my noise margin? It is minimum of noise margin high or noise margin low. So what is the minimum of those two values? Minimum of 4.06 and 0.5. So that thing is equal to 0.5 volts. Now the second part was asking us to calculate the transition width. Transition width is simply equal to VIH minus VIL. So that is equal to 0.94 minus 0.7, that is 0.24, and also the logic swing, that is equal to VOH minus VOL, that is 5 minus 0.2, that is 4.8 volt. This is a swing. So my values are 0.5 volt, 0.24 volt and 4.8 volt. 0.5, 0.24, 4.8, 0.5, 0.24, 4.8. So option A is the correct answer to this question. Now moving forward to the question number 17. Question number 17 asks, the figure of merit of a logic family is given by the product of A, gain and bandwidth, B, propagation delay time and power dissipation, C, fan out and propagation delay time, and 4, noise margin and power dissipation. This is a theoretical question. So the figure of merit of the logical family is always given as a product of propagation delay time TPD, and the power dissipation. So for a circuit, for a logic family, it should be as small as possible. So what is the typical units of propagation delay is in nanoseconds, and power dissipation is in millivolts, and we get the delay in picojoules. So at the end of the day, it tells us about the energy consumption, so we want it to be as small as possible. So the figure of merit of a logical family is given by this product. It's also called power delay product, PDP. Now question 8. A particular logic family has VOH equal to 5 volt, VOL equal to 1 volt, VIH equal to 3.5 volt, and VIL equal to 2 volt. The noise margins NMH and NMR. So we have done this question in, I think, question number 16 was around these lines. So noise margin high is simply equal to VOH minus VIH. So VOH here is 5 volt and VIH here is 3.5 volt. So this is 1.5 volt, and noise margin low is equal to VIL minus VOL. VIL is 2 volts minus VOL is 1 volt, so it is 1.5 volt and 1 volt. So option 1 is correct. Now the question asks, the logic gate implemented using the circuit shown below, where V1 and V2 are inputs with 0 volt as logic 0 and 5 volt as logic 1. V output is, so we have to find the functionality of this circuit. So let's just consider when V input is, so let's just consider when V1 and V2 are both 0. So when V1 and V1 are both 0, so Q1 and Q2 are both off, so V out is connected to logic high, so V out will be equal to high for inputs 0 0. So when input V1 is equal to 0 and V2 is equal to 1, so this will be on, so V out will be equal to 0. And also when V1 is equal to 1 and V2 equal to 0, V out will again be equal to 0. So this is 0 for 0 1 1 0, and when both of them are equal to 1 1, so again the output will be equal to 0. Both of them are on, and the output will be equal to 0. So what is this? When output is equal to 0 0 for 1, So output is equal to 1 for 0 0, this is v1 v2, 0 0 0 1 1 0 and 1 1, and for 0 1 it is 0, for 1 0 it is 0, and for 1 1 it is 0. So this is simply a NOR gate. Now going to the last question of this today's live session. So in the given transistor logic collector circuit below, IOL max is 16 milliamps. What should be the minimum value of resistor R to prevent the damage of the output transistor? Consider VA equal to 5 volt. So what we do here is, so we have to find the value of R to prevent the damage. So what will be the worst possible case? The current, what will be the maximum current that will go through this R is simply IOL max. So this is the worst case scenario where IOL max is 16 milliamp, and this 16 milliamp will all go through this resistance. So this is the worst case scenario, and we have to design according to that. So we have this 5 minus 0.2 where the transistor is in saturation region. 5 minus 0.2, R is equal to 5 minus 0.2, 5 minus 0.2 divided by the current IOL max. So R will be equal to 5 minus 0.2 is 4.8, IOL max is 16 milliamps. So I'll be getting output in K's, kilo ohms. So 4.8 divided by 16, this is 0.3 K. So that is R is equal to 300 ohms. So option B is the correct answer. So this was for all for today's session. I know there are some questions to be repeated, so let me just check the chat box first. Then I think question 9 and 10 need to be repeated. So question 18, how many questions are now for discuss? I think I had an internship karna, any faculty continental. So I don't have that thing, but you can refer to department sites of the various institutes. You can refer to the department sites, so where you can what should I say, you can refer to the department sites. I think you are from electrical, you can refer to the department sites of electrical engineering of various institutes. So apply, just write a well decorated mail along with your CV and send it to the professor of your interest. So if he or she is interested, they can mail you back and you can get an internship opportunity. That's how I got my internship opportunity. When I was doing my bachelor's, I wrote a email, sent my CV and all, then I got a reply. So regarding today's notes, everything will be shared by NPTEL team. They will share, everything will be shared. I'll just uploading them to the Google Drive, and they will share you the link of that Google Drive containing the video link as well as the notes. Everything will be shared. So someone has asked me to repeat question 18, and I also think question 10 was asked to be repeated. I'll just go through them quickly. Question 18, where is it? Question 18, which one is question 18? Okay, question 18 was pretty simple. So it asks us to find the noise margin. So noise margin high and noise margin low. So we simply know that noise margin high is VOH minus VIH, and noise margin low is VIL minus VOL. These values are all given. I just plugged in those values and I got these answers, 1.5 volt and 1 volt. Also question 10 was to be discussed again. Question 10 and no 9. Question 10. So consider below circuit. So when any of the input is 0, this diode will be turned on and this output will be connected to the ground. So my output will be 0. Any of the input combinations, when any of the input is 0, the diode will be turned on, my output will be connected to low voltage, approximately equal to 0 volt. And when all of them are equal to 1, these all are reverse biased. So these will be all open circuited, and my output will be high, driven by this voltage source. So my output will be equal to high. So for input combinations where any of the inputs is 0, my output will be low, that is V0 equal to 0 for any of the inputs having as 0, and my output will be equal to high when all of the inputs are high. So that means V0 is equal to 1. So this was the functionality, and this corresponds to the AND gate. So I think that should be enough for today's session. So Kailash, I can't discuss anything regarding that. So first of all, I have not prepared that lecture, and also flip-flops will be discussed in I think week 7 and 8. Let me just put the course contents. Week 7. So in week 7 I'll discuss flip-flops, and also these lectures will be uploaded on my YouTube channel. And last year I was conducting digital circuits course. There I also discussed these along these lines, the problems related to weekly assignments. I would discuss those. So if you want to refer problems related to flip-flops, you can go to those lectures. And other than that, you can refer to your class notes, you can refer to the books, you can refer to the lectures on NPTEL, previous year NPTEL courses, or you can refer to the YouTube videos. But I won't be discussing here, that's for sure. I won't be discussing flip-flops right now, but in week 7 I will be definitely discussing them. So it's my name, simply Musab. These are just simply there I'm also solving these questions. They are not anything special. I'm just solving the questions there. That's all. The course was digital circuits. It was conducted from August to October. And regarding today's lecture, everything we made available, from lecture videos to lecture notes, everything. But I think you might have to wait for a couple of days. I'm not sure about that. They might even upload it today only. But from my end, I'll be just giving them these things within half an hour. So thank you guys. This was all for today's lecture, week 1 lecture. My name only. This is. Thank you for coming. Hope to see you next time. Thank you.